It's here today.
Oh, really?
Approach. It's like it's red. Today's like. I beg mistake for something about wrong and it's like your thanks very much. Like that was probably one of the last. He's like not like
Seems like
stuff like like you like I put around yeah. They're like oh yeah. Feels like an accident.
Okay,
It's fall.
get started. I'm excited about today's lesson. Today I get to duck you into the, I understand Newton's third law club. As I said before, it's not a large club. I'm so excited that I woke up at 4 in the morning and went back to sleep. So if I fall asleep during lecture. Take over.
Professor, I think your mic isn't working.
Mic is not working.
I don't think it's on.
Is it working now? Better? Okay. Hello. Would someone be willing to give us an opening prayer to get us started on this lecture? Anyone? Thank you, good sir.
Our Father in heaven, we thank thee for this opportunity we have to learn physics and to study at the university. We ask for the Spirit that it may help us understand physics and that we may be grateful for the chance to learn here and that we may respect Dr. Francis's time, and please help us to remember what we go over and that we'll get help if necessary and that we can keep the Spirit with us. And we say this in the name of Jesus Christ, amen.
Thank you. Pray for me. Okay. And last day, we did a very, very simple exercise that convinced us, I hope, that force is what causes acceleration, not velocity. We've got to ignore the velocity vector. Sometimes the force is in the same direction as velocity just by coincidence, but that's not physics. It's always in the same direction as the acceleration. And we introduced Newton's second law, which is the most important piece of information that goes in your toolbox. Okay, the net force causes the acceleration, and by net force, we mean the mathematical sum, the total of all the real forces. For example, this example of the dry ice going down the ramp, we drew a free body diagram for the dry ice. The first force we put on any diagram is the weight down towards the center of the earth, and we label it Earth by the earth on the block. Then we ask, are there any magnets in this problem? No, be patient. So, what touches the block? Well, the ramp. Does it push or does it pull? Not a rope, not a string, not a thread, not a chain, so it must push. Whenever one thing pushes on another, there will always be a normal force. By normal, we mean perpendicular to this surface between the pusher, the ramp, and the pushee, the block. And that would be the normal force by the ramp on the block. I then ask, is there a friction force? Well, no, it's coasting on a layer of gas, so we get rid of the friction. So that's the free body diagram. I followed the recipe. Now the question is that acceleration that it experiences caused by the weight force or by the normal force? And the answer is both. Okay, we have to take them and add them as vectors. There's the plus sign right there, head to tail. And then the net force or total force is just from the first starting place to the last ending place, kind of like the walk in a park problems that we had on the last exam. Now, the acceleration is always going to be in the same direction as the net force that causes it. And so that's going to be down the ramp, which is what we've known since the first tutorial. Now, we had this pretest on Tuesday, and the last question on that pretest, no, we'll take care of the last question at the end of today. Let's look at the second question on that pretest. We were asked to compare the force by the snow up to the weight of the crate down. And the question was, is it going to be bigger than the weight, equal to the weight, or less than the weight? Let's use our clicker. We all know what the answer is. We should get a perfect 100% on this.
Good is the key word.
Now you can click. Get that clicker out. Humor an old man. Everybody get this right, okay? Let's just, so that I can brag in the nursing home. Yeah, my students got it all right. Okay. Okay, last call. Get her done. Whoa, 9 people stabbed me in the back. Okay, the answer is A. Okay. So the trick is to ignore that velocity vector. It never matters. We don't care what direction it's traveling or how fast it's traveling. We care what the acceleration is. And unfortunately, that vector is a little bit more difficult to figure out. If the acceleration is up, this free body diagram has to scream up. Okay, has to scream up. Now, putting it all together, we needed the concept of mass. And last day, this demo just went terribly, terribly wrong. We caused all sorts of havoc. I think there's going to be a stain here. So I decided I'd just quickly do it again, just so that it can go terribly, terribly wrong again. Okay. Now you notice that the things that had little mass, they took off, but the things that had more mass stayed behind. And that's what we wanted to see. Okay, that is a pity clap. That is a pity clap. And I know a pity clap. Okay. We found that the acceleration was proportional. That's what the fish symbol means. Proportional to the net force divided by the mass. We found that with those 2 experiments that we talked about. And we can always replace a proportionality with an equal sign as long as we put in a constant of proportionality. This equation on top just says that if I double this on the right, I double this on the left. But it doesn't say they're equal, okay? And so if I put in that constant, doubling this will double that, but they're not necessarily equal. But I get to choose my units, and that will change what my constant is. I've already chosen meters per second squared for acceleration and kilograms for mass. In Murica, the force is measured in pounds. But if we choose a different unit, namely the Newton, then I can make this constant go to 1. Okay, so a Newton is the force required to take 1 kilogram and make it accelerate by 1 meter per second squared. Now, if I do that, if I choose my units to be in newtons, I get my my equation in this form that we call Newton's second law. And that's the equation that you're going to need for this second exam. That's it. Okay, that's the big one equation to rule them all and in the darkness bind them. Okay, that's the one. Okay, now we need another piece of information. I have a spring scale here that measures forces in newtons. As you can see, it's not the most expensive piece of equipment in the world. This one came over, I think, with Brother Brigham. I'm trying, there's a whole lot of stuff in the demo room that came over with Brigham, and I'm trying to replace it as I can. So the question is, if I hang this 1 kilogram mass from this spring scale, what's the reading going to be? And maybe you know, maybe you found out in a previous class, but the answer, it turns out, oh man, this is really, the answer is around 10, okay? If I had a really, really accurate scale, it would read 9.8. If I had an even more accurate scale, it would read 9.81. But if we're on that other planet where the acceleration of gravity is exactly 10 meters per second squared, I would get 10 newtons there. And if I were to hang 2 kilograms by putting another one on there, I think you can guess what that's going to be. That's going to be 20. Okay. Simple enough. We spared no expense. Okay. Now let's talk about what that scale is actually measuring. That scale can only measure how hard it's pulling up on the masses and how hard they're pulling down on the scale. But if we remember what we just learned about Newton's second law, if these masses aren't going anywhere, then this free body diagram has to scream balance. And that means that that tension force that is the reading on the scale is indirectly measuring that gravitational force of the earth pulling down on the masses. And so indirectly, we're measuring the weight force. Now, what that gives us is if we assume a gravitational strength of 10, 9.8 really, we're calling it 10, then we can find the weight force, which is the first force we put on any free body diagram. We can find that just by taking the mass in kilograms and multiplying it by 10. 10 newtons for each kilogram. For each kilogram. Now, if I ask this question, if Greg jumps off the physics building in a vacuum, what will his acceleration be? You're all going to scream out 9.8. We know this already. Let's call it 10 meters per second squared. But let's use Newton's second law. Newton's second law requires first that we draw free body diagrams. And when something's in free fall, that diagram's very, very simple. It only has one force on it, the gravitational force, because the object's not touching anything. That's what we said free fall was. Now, if I use Newton's second law and I ask, what's my net force? Well, that's like asking, what's your net worth if you've only got one bank account? Well, that net force is just going to be the one force I've got. Okay? And now, if I use what I just learned, that I can write that weight force as the mass times 10 newtons for each kilogram, and I plug that in for the weight force, here's the magic. The mass cancels out. And it doesn't matter whether we drop Greg off the physics building or whether we drop the grand piano off the physics building. They all speed up at 9.8. We're going to call it 10. Wait a minute. I was expecting 10 meters per second squared. But instead I get 10 newtons for each kilogram. And that's the same, okay? That is the same. If I look at what a newton is, think about F net equals ma. The left-hand side of that equation is in units of newtons. The right-hand side is in units of kilograms times meters per second squared. Well, a newton per kilogram would then be a Newton is just a kilogram meter per second squared. If I divide that by the kilogram, I get meter per second squared. They're equivalent. When I'm talking about something speeding up because I drop it, I use meters per second squared. But when I'm looking at how hard the earth is pulling down on some mass, I use newtons for each kilogram. See if your neighbor is in the ballpark of understanding.
But you're there. So much about.
I think so, yeah. Yeah.
Nice.
Okay. What that means is that we can always, with every problem we work, put a weight force on very first, and we just take the mass and multiply by 10 to get the number of newtons for that weight force. It's just M times G. That's the other piece of information you'll need in your toolbox. Now, when I was a young person, the original Star Trek was brand new. I mean, it was amazing. They could talk to people on a little thingy they held, and they could walk towards the door and it would open by itself. It was amazing. Blew our minds, actually. But one of the things that I just couldn't get around was the fact that they traveled throughout the universe, and wherever they went, people spoke English. That didn't seem real to me. Everything else was fine. That I had problem with. Until they explained to me that they had those little badges on their shirt. And that, it turned out, someone explained to me, was a universal translator that took whatever those people were speaking and turned it into English. And then I was fine with it. Well, it turns out that in physics, there is a universal translator, and it's Newton's second law. It translates between the forces, the dynamics, and the motion, the kinematics. And I'm going to show you with two examples, one of which is a homework problem. Okay, you're welcome. The first problem, we have a 5 kilogram mass being pulled by 100 Newton tension force in a rope. And the result is an acceleration of 4 meters per second per second. Okay, and the question is, how big is the friction force? So in this case, we're giving you the kinematics, the motion, and we're asking you to find the dynamics, one of the forces. Well, the first step in any dynamics problem is a free body diagram. And the first force I put on that diagram is always, always, always the weight force, Earth on the block. And now we know how big that is. We just take the 5 kilograms, we multiply it by 10, and we get 50 newtons. And that's it, okay? Then I ask, are there any magnets in this problem? No. So what touches that block? Well, the rope and the floor. Well, the rope pulls with a tension force, and the floor pushes. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. In this case, we're asked how big the friction force is, so there must be one. That's the free body diagram, and I know it's correct because I followed the recipe. I'll always get the right free body diagram if I follow the recipe. Now, as soon as I get my free body diagram, I get to use Newton's second law twice, once in the y direction and once in the x direction, okay? In the y direction, I don't have any acceleration, and so I don't have any net force in the y direction. My diagram has to scream balance in the y direction, and that means the normal force is 50 newtons, okay? But in the x direction, it doesn't scream balance. I know that it's got to scream to the right because the acceleration is to the right. And the diagram always screams the direction of the acceleration. But how loud should this diagram scream to the right? Well, the answer to that is always given by Newton's second law. F net equals ma. Well, the scream is the net force, okay? And the net force is, we got to take 5 kilograms and accelerate it by 4 meters per second squared. That gives me a scream of 20 newtons to the right. Well, how big does the friction force have to be so that I have 20 more newtons to the right than I have to the left? Tell your neighbor real quick. Yeah, it's got to be 80 Newton. 80 Newton. Now, if you'd rather, if that scream method doesn't speak to your soul, maybe you could use just what we call the maths. The net force is just the sum, the addition of all the forces in the x direction. Well, Greg, your mouth said add them up, but your screen says subtract them. I'm adding them as vectors. The tension force is to the right, so it's positive. I add it as a positive value. The friction is to the left, so I add it as a negative value. And if I plug in what I know and solve for F, I get 80 newtons, like we found before. Check that your neighbor followed that. Check that your neighbor's okay.
We figure it
I can.
Okay. This problem is just like one of your homework problems. You're going to have a different value for the mass of the sled, but other than that, it's the same problem. We have this sled and we're pulling it again with 100 newtons, but this time there's a wrinkle. That 100 newtons isn't in the x direction. It's at an angle, a goofy angle, happens to be 37 degrees, okay? And we are told that the friction force is 50 newtons. And we are asked to find the other forces acting on the sled and the acceleration of the sled, okay? So in this problem, we are given the forces and we are asked to find the acceleration. Given the dynamics, the translator is going to give us the kinematics, the motion, okay? Now, the first step is always the free body diagram. The first force on that diagram is a weight force. And because I've got 15 kilograms, I have 150 newtons. You're going to have a different value there. That's all, okay? Then I ask, are there any magnets? Be patient, they're coming. What touches that sled? The rope and the snow. So the rope pulls along the direction of the rope, and the snow pushes with a normal force. By normal, I mean perpendicular to the surface of the snow. And there's a friction force that I know is 50 Newton. Yes.
So once we're going up this incline, why is the normal force in like the vertical up direction instead of like out this way?
Oh, normal means perpendicular. And since it's the snow pushing on the sled, perpendicular to this surface would be straight up.
What?
Okay. So if I put something on the table, the normal force on that something would be this way. If I picked up the table so that it was at a ramp, at an angle, the normal force would be perpendicular to the table. It's always perpendicular to the surface. Normal just means perpendicular. Now, what makes this problem different from the last one is that goofy tension force. It's not in the x direction and it's not in the y direction. And whenever you get something that's not lined up with your coordinate system, you have to break it up into its parts, into its components. And because this is 37 degrees, this is going to be a 3, 4, 5 triangle. This is going to be 3 times 20, 4 times 20, 5 times 20. Everyone see that? We've been there before. Now, what you see there is that we didn't get to just walk away from vectors. Vectors are going to be a big part of what we're doing with dynamics and the rest of the semester, actually. Now, as soon as you break up this force into its components, you throw away the original and use the components. That's important. Now, again, we get to use Newton's second law twice. Since the acceleration I know is all in the x direction, it's not levitating up and it's not digging itself down into the snow, the acceleration in the y direction is 0. And that means my diagram had better scream balance in the y direction. Well, tell your neighbor how big that normal force has to be in order for the diagram to scream balance in the y direction. Yes, sir.
We already have 60.
Oh.
Uh, we're not adding them as numbers, we're adding them as vectors. And I could take 80 and 60 and get 20 out of it, you know, or I can get 100, or I can get 140. It all depends on what that. If you take your ruler out, that's what that gives you.
Instead of saying has no y.
Okay,
We're saying it needs to balance.
I hope that no one said this has to be 150. It has to be 90. Because all the force up has to balance all the force down. But I've got two forces up. And 90 plus 60 gives me 150 up, and I've got 150 down. So it balances in the y direction. Now, in the x direction, it doesn't balance. I've got 80 to the right and only 50 to the left. That's a net or extra of 30 to the right. My screen is 30. And that 30 is going to be the mass of 15 times the acceleration. That tells me the acceleration's got to be 2 meters per second squared. But we can also do it with the math. If we plug in the math, my T sub x is positive because it's to the right. My friction is negative because it's to the left. And I've got 80 minus 30, 80 minus 50 is equal to the mass, 15 kilograms, times the acceleration. When I solve that, my calculator, I get 2 meters per second squared. Again, check with your neighbor, make sure that they're able to do these dynamics problems. Now, folks, there are an infinite number of dynamics problems, a whole host of different ways that I can dress them up. But they're all this problem. This is it. This is all we got. I wish there were more that pay me more, but that's it. That's the dynamics problem. Okay? And we're going to be practicing that over and over again from now until the next midterm. Okay, now we're getting to what I'm excited about. Newton's third law, my very, very personal favorite. I believe that Newton's third law is the most beautiful physical law in the universe. Okay, it is so elegant and yet so misunderstood. And so we're gonna do our best to understand it. The first thing we need to do is understand what we mean by force. And perhaps we'll just go to the dictionary here. Webster says power of energy, strength, the force of a gale, power exerted on any resisting person or thing. Does that seem helpful? No, that's just a bunch of highfalutin words put together, absolutely worthless. Perhaps something more spiritual. Trust the force, Luke. Also not helpful. Okay. What we need is an operational definition. And you remember that operational definitions are a recipe that we use to actually measure, to get a number for what it is we're defining. Okay? Now, your gut tells you that a force is just a push or a pull. So if we're trying to define operationally a pull, what's your name, sir? John? That's easy. I can remember that. I pull on John, and he's pulling on me. And I want to operationally define that pull on John. And what I would do is I would take a spring scale, and John and I were pulling, and I would just quickly slide that spring scale in, and we're going to pull again, okay? And the reading on that spring scale is going to be, in this case, the pull by John on me. Now, if we wanted instead the pull by me on John, I'd just slip it around, okay? And we'd do the same thing. And here's Newton's third law. We would get the same reading either way. Either way, we'd get the same reading. Thank you, John. Okay, now, what if instead I have a push? Well, then I would use a bathroom scale. If I'm pushing on this wall and I want to operationally define how big that push is, I would just remember how I'm pushing and slide that in there, and the reading on the scale would be the definition of that push. Now again, that's the push of me on the wall. If I wanted the wall pushing on me, I would have to turn that scale around and slide it in this way. And if the wall had eyes, it would be reading what the scale said right now. And here's Newton's third law. We would get exactly the same number. Exactly the same number. That in a nutshell is the third law. Now, what about the direction? Force is a vector, so it has direction. But here we just use our gut. It's obvious. If John and I are pulling on each other, the pull on me is that way. The pull on John is this way. Okay, that just, you feel that. Okay. Now, how many of you have seen the movie Groundhog Day? Yeah. If you don't have your hand up right now, you got to watch that movie in between sessions of conference this weekend, okay? That's a classic. And you remember that he's stuck in Groundhog Day over and over again. Every day he wakes up and it's the same day and the same things happen. And he has to live that day over and over again until he finally gets it right, okay? Now, suppose for an instant that I am stuck in Groundhog's Day, okay? And I notice that at 4 o'clock, there's a collision between a little red car and a great big truck. And I've been thinking about Newton's third law, and I'm really wondering whether it's true. And so at 4 o'clock the next day, which is the same day, which is Groundhog's Day, I'm on the side of the road with my bathroom scale. And right before they collide, I slide the bathroom scale between their bumpers so that the woman in the red car can see it. And she goes, "Oh my." Okay, big number. Now the next day, which is Groundhog's Day, the same day, at 4 o'clock, I'm back on the side of the road with my bathroom scale. But this time, I slide it between the bumpers so that the trucker can see it. Oh my, big number. Which one sees the bigger number? Yeah, Newton says they saw the same number. It's part of the same interaction. But do we have to believe that? I mean, Newton's been gone for a long time. That just doesn't seem reasonable. What if I told you that the truck was speeding? What if I told you the truck was loaded down with gold and that's why I was on the side of the road? Okay. Is it still going to be the same force? Well, let's find out. We have an opportunity to find out. I have 2 carts here, and those carts have force probes on them. And I'm going to use those force probes. I'm going to, let me just show you what they do. So this one goes up and this one goes down. Okay, I just reversed one of them. And now let me zero that out because I messed with it. Okay. Now, well, that didn't work. There we go. Okay. Now I'm going to blow that up. That's pretty convincing, okay? I mean, there are some irregularities because of the technology, but that's pretty much the same complicated force on the left one as on the right one. Now, in 1998, when my friend Jeff Adams and I were team teaching this course, this technology first became available. Veneer Software came out with these force probes, and we had them delivered to us, and they showed up the very morning we were going to teach Newton's third law. And we decided, hey, let's just try it in class. We don't have time before. Let's just do it during class. And we rammed those cars together, and we got that experience there. And Jeff and I just looked at it and said, oh, it's true. We taught it for years, but we didn't believe it. But it was true. And then the rest of the lecture, it was just, the lecture stopped. And what we did is we loaded up one with a bunch of weight, we rammed them together, and then we took the other one and made it go fast and rammed them together. We parked one and rammed them. We could never get them to be different from each other. It's just so exciting. Physicists are so easily amused. Okay. Now, I put this in here in case the technology didn't work, and I needed, this is just taken last year, okay? Now, can you quote Newton's third law? I'll get you started. For every action, there's a equal and opposite reaction, okay? For every action, there's an equal and opposite reaction. Now, John hasn't really been paying attention, and that ticks me off. And so I come and, pow, action. Well, John hasn't been slugged by a professor, at least not during a lecture, and he's pretty upset. And so after class, he's waiting in the hall, and as soon as I walk out, pow, reaction. Is that what Newton's talking about? No. At the very instant that my fist hits John's jaw, what? His jaw's hitting my fist. Which one of those forces is bigger?
Same.
We just saw it. They're the same. What that means is at the very instant that I hit John, we're even. This has, yes, sir.
I feel like something confusing about.
Wait. What?
I feel like something confusing about this though is that like even though the force may be the same, the effect that those forces will have.
That is exactly right. It
Yes.
hardly even affects John's jaw because he's strong, and it totally crushes my hand. The effects will not be the same, but the force in newtons will be exactly the same. Thank you for bringing up that observation. Thank you. Now, this has terrible implications for parenting. When our children were young, I was in the kitchen, and my youngest, Matthew, came running in with tears streaming down his face. Just, Josh hit me, Josh hit me. His big brother Josh came running in after him. You hit me back. I did not. Yes, you did. Third law. What could I do as a parent? Josh had truth on his side. Now, because of this language, action, reaction, we often think that one of those forces is a little sooner or a little bit more important. But that's not true. So I like to say it this way. If a red object pushes on a blue object, the blue object always pushes back with a force that is equal in strength and opposite in direction. So here's an example. The red car and the blue truck, there's going to be a lot of forces on the car and a lot of forces on the truck. But one of those forces on the car will be a normal force by the blue on the red. One of the forces on the truck will be a normal force by the red on the blue. If you take away nothing else from this lecture, you should take away this. In the entire universe, there is no such thing as a single force. all forces are married. Marriage is what brings us together today. What's that from?
Right.
Princess Bride. If you haven't watched that one, watch that one this weekend too, okay? All forces come in a set, in pairs, okay? And this is how you recognize those pairs. There's three ways. The first way is that they're part of the same interaction. So if one is a normal force, the other will be a normal force. If one's a friction force, the other one will be a friction force. If one is a tension force, the other will be a tension force. The second way, they have the same indices reversed. This is red on blue. That's blue on red. You can almost see those indices get up and pirouette and come back down. The third way is that those companions, those married forces, will never, ever, ever act on the same object. One of them is acting on the blue truck, and one of them is acting on the red car. They're never going to show up on the same free body diagram. Again, one of those forces was hurting John's jaw. The other one was breaking my fist. They're never on the same object. See if your neighbor now understands Newton's third law.
Right. Bounce off each other. If same.
We have a married couple in the class. Is anyone in here a married couple? Oh, okay. Come on down, you two. We're gonna have Family Feud here. Okay.
Well, it was this way. Set this up. They just. They're good
Okay, if I could get you to face off with each other and each hold one of these force plates. Okay. And when I say go, I'd like you to just push them together and just kind of try to push your partner out of the way. And, okay. And, let's get them start. Okay, you can start. Oh, that's not working. Oh, just a second. Hold, let's be patient. I gotta do that. Okay, let's try it again. Okay, go. That's not helpful. Oh. It worked this morning. Let's just turn them all on. Okay. Try it one more time. Whoa. Oh. Oh. Okay. At first, tell me your names.
Seth.
Jeff?
Seth.
Seth.
Yeah.
Stace? Sage. Seth and Sage. Sage and Seth.
Yeah.
Great. Okay. Let's give them a hand, folks. It looked like Seth was more powerful than Sage. And as someone who's been married for 48 years, I'm here to tell him, you're going to find out that's wrong. But no matter how strong he is, he could have been Arnold Schwarzenegger, who you're too young to know who that was. But, if we got Arnold Schwarzenegger and Mary Lou Retton pushing off it against each other, they're going to be exerting the same force on each other by Newton's third law. They will always have exactly the same force, but in the opposite direction. Okay. Now, I think it's time for a concrete example. So let's take the example of a rocket ship on a concrete launch pad. And we blast off 5, 4, 3, 2, 1. Looks like that. And my question for you is, what thing is pushing on the rocket? All macroscopic forces are exerted by something that you can taste, smell, touch, on some other thing that you can taste, smell, touch. So what thing is pushing on that rocket? And second question, is this a contact or a non-contact force? Now, think about those two questions while we do this next demo. And normally, the next demo would be me rocketing across the room with a fire extinguisher. But it turns out that I have asked the fire marshal here at BYU if I could do that demo, and the answer was not no, but heck no. And so what we're going to do is watch a video of Greg doing it in Montana, where you can do anything. We're going to actually do this. Yeah, that's what I'm talking about. Okay. Rocket Man. Okay. I need a countdown. 5, 4, 3, 2, 1. This demo has not always gone well. That demo has not always gone well. My first year teaching, that was 33 years ago there. I was on this stage that had a brick wall on both sides, and I got going really, really fast across, and I needed to stop. So I decided to use air brakes, and I turned my fire extinguisher around to hit the other wall, and I forgot to turn it off, and I took out the front row. Just books and everything just went flying. The other time, I was going to an elementary school, and I was in their gymnasium, and I wanted to blast that fire extinguisher. Well, our department had 2 fire extinguishers, one that had a blast going straight and one that had it going at 90 degrees, and I forgot which one I had. So I hit the lever, it hit me in the head, I landed on my back with the fire extinguisher on my chest. It turns out 3rd graders like that stuff. That was the best part of their day. That was great. Now, my question is, at the front, at the first of it, I had that wall to push against. But once I got in the middle of the room, what was I pushing against? The air? Well, let me ask you this question. What if I close the doors and suck all the air out of the room and start in the middle of the room and hit that fire extinguisher? Do I go anywhere? Oh, yeah. If you saw the movie Apollo 13, they're stuck in outer space. There's no air to push against. They hit their thrusters and they go. Or maybe if you didn't see that movie, maybe Wall-E, where he's got the fire extinguisher and he's going around the ship. You've got to watch a lot of movies this weekend. We don't need the wall. We don't need the air in the room. We don't need the concrete launch pad. That launch pad just keeps the rocket out of the mud, okay? What we need is Newton's 3rd law. Newton's 3rd law is the foundation of all rocket science. That fire extinguisher is pushing the gas that way, okay? And by 3rd law, if the fire extinguisher is pushing the gas that way, then the gas is pushing the fire extinguisher the other way. And that's what causes the rocket to go. Now, I did not always fully understand that, okay? When I was a teenager, I had this misconception that NASA needed that launch pad. It needed that good, solid boost to get it going. Now, I had a neighbor, his name was Paul Junkie, and we were both geeks. And we did a lot of different experiments that involved rockets. We got these little toy rockets with the solid fuel pellets. And I told Paul, I said, it's a shame that NASA can't bring the launch pad with them. So I had a brainstorm. And I went into the house and I borrowed, by which I meant stole, a pie pan and attached it to our rocket. And then I went back into the kitchen and I borrowed, by which I mean stole, a second pie pan and bolted it to the first so that we could take our launch pad with us. What does that look like to you? A bomb. Yeah, that's exactly how it worked. Yeah, this was not one of our finer moments. Okay, we did not need that launch pad coming with us. Okay. Let's look at this problem. You apply to business school, and this is the entrance exam. They put you on a large pond of frictionless ice, and they give you a great big bag of gold, and they say you've got to get off of this this pond of frictionless ice. What do you do to? Because you can't walk off without friction. You're not going to go anywhere. You're just gonna, your feet are just going to slide back and forth. What do? Tell your neighbor. What do you do?
Go to the bag.
Picture doesn't even go.
Okay.
I shoot anything else, but.
If your neighbor said, throw the gold, they failed the entrance exam. A business major is never going to let go of that gold. Okay. That's just the wrong attitude. Okay. A business major will strip naked and throw their clothes before they let go of that gold. But what if you keep your clothes on? Is there a way to get off of that pond? Let's think about it. Hold on to the gold and maybe that doesn't work. Yes, sir.
Take your tie, head to the bag, and when you throw the bag, you just hold on and let the bullet hold you.
Say what?
You take your tie off.
Ah, the tie.
Then it'll pull you.
Yeah, you tie the tie to the gold and you throw it and then just let it drag you along. He gets in the business school. He wanted to go to med school, but now he's got to go to business school. Okay. Here's the poor Gary problem. Gary has a major problem. After studying Newton's third law in his physics class, he's convinced himself that it's true. Unfortunately, he's convinced himself while sitting in a closed room with a single door. He reasons to himself, if I push on the door to go out, Newton's third law tells me that the door is going to push back with an equal force. That force is going to cancel the force that I push with. Even if I push as hard as I can, that door is going to push back just as hard. Oh no, I'm stuck in this room. I never should have studied physics. Now, clearly, there's something wrong with Gary's reasoning, because he can go and open that door and leave the room. We know he can't. But what is the flaw in his reasoning? Talk to your neighbor. What is he missing here?
Yeah. You guys have any opinions? I had a couple like. So, because you can push a door this weighs more than you. I think that's to do with all the
pre-diabetes.
Yeah, I push you. Or might not.
Your arms break the door.
Okay, brave soul, raise your hand. What's the mistake here?
That there's static friction.
I'm sorry?
Is it that there's static friction?
Oh, friction. I should have told you this. That's my fault. I thought that's on me. It turns out that the janitor was there the night before and he had polished the floor with a new wax called frictionless. Gary pushes on the door. He goes sliding this way, but the door still opens. So that's not it. Brave soul, where are you? Back here. Oh, it's Seth. He wants to redeem himself. The eyes of his woman.
There's a lot more forces acting on objects here than the door.
Oh, Seth. Oh, this is on me again. I forgot to mention, just by some quirk of coincidence, he has exactly the same mass as the door. Who saw that coming, huh? Who saw that coming? What else could it be? Yes, sir.
The forces don't cancel each other out.
They don't cancel each other out? Well, if one is 50 newtons this way and one's 50 newtons that way, how can they not cancel each other out? Oh, say that louder, please.
Each other in different ways.
Okay. Say it loud.
The forces are acting on each other in different ways.
Are they acting on each other? What are they acting on?
So it's on the door, but the door's pushing on.
Okay, so one of those is acting on the door and one of those is acting on Gary. They can't cancel because they don't appear on the same free body diagram. One of them is breaking John's jaw and one of them is breaking Greg's fist. They act on different things. So if I draw a free body diagram for the situation, I've got the door, and there's going to be weight down on the door. There's going to be a normal by the hinges on the door. And then there's going to be this force, a normal force by Gary on the door. And if I want to draw a free body diagram for Gary, there's the weight down. There's going to be the normal by the floor on Gary. There might be friction. We said that there wasn't, but maybe there was by the floor on Gary. And then there's this force that is a normal by the door on Gary. And these are third law companions. These are a married set. When this one gets bigger, this one gets bigger. But they can't cancel each other because they never appear in the same formula. When I used F net equals MA on the door, this is the mass of the door, the acceleration of the door, and the net force is all of these forces. Okay? If I want to know about the motion of Greg, or Gary rather, I use F net equals MA. This is going to be the mass of Gary, the acceleration of Gary. It's these forces that go into the net force. They never appear in the same formula, equation, so they can't cancel each other out. The most famous version of this question is the horse and the cart. You've got a horse pulling a cart through Central Square in New York, and the question is, if the cart's always pulling back on the horse, just as hard as the horse is pulling forward on the cart, how do they get anywhere? And the answer is, only one of those two forces is acting on the cart to move it through the park. The other force is acting on the horse to make his day hard. Okay, see if your neighbor follows that logic, that reasoning.
Get it?
There's no. He's still, he's one of the kids who just. And he's like, oh.
Okay. On the MCAT, every now and again, they put the famous bug problem. A bug splats on the windshield of a car moving at 100 miles per hour. Which feels a greater force, the car or the bug? What's the answer? The same. And yet people always miss this question because they're answering a different question. And that's which one had the worst day? Okay? And that's this concept about the forces being the same, but the effects are not the same. Yes, sir.
Why don't you, when you pushed on the door and you drew those diagrams, why don't you accelerate backwards though? Because the force of the door on you is greater than the little bit of friction that we did allow.
Oh, I drew that friction force to be small, and if that were the case, I would rebound. I would, yeah. But in truth, and we're gonna learn about friction on Tuesday of next week. There's gonna be enough friction with this rug that it would balance
Okay.
that out. Yeah. Okay. Now, another version of this is when I drop this pen, the earth is exerting a gravitational force on it, and that's causing the pen to speed up by 9.8, call it 10 meters per second every second. Okay. But Newton's third law says that whatever force the earth is pulling down on the pen is also pulling up with that same force on the earth. So why doesn't the earth just rush up to meet it when I drop the pen? Well, again, the mass of the earth is so huge that that little force isn't going to do diddly to the earth, but it's big enough to make this pen speed up by 9.8 meters per second. Okay? Now, let's look at your tutorial homework. This is one of the more difficult problems on the tutorial homework. You have a chain made of 4 identical links, and you're asked to draw free body diagrams for each of the links. Now, the first force you put on a diagram is the weight force, and because those are identical links, the weight's going to be the same for each link. I'm going to make up a number. I'm going to call that 3 newtons. 3 newtons, okay? Now, when you are asked to draw free body diagrams for multiple objects, this is a trick that you should put into your toolbox. Always draw the free body diagram of the simplest object first. And by simplest object, I mean the object that's touching the fewest other things. So which free body diagram do I start with? 4, okay? So there's no magnets in this problem. I've already put the weight force. What touches link 4? Link 3. Well, does it push or does it pull? Well, that kind of depends on how you look at things. If you look from a distance, those links are pulling on each other. But if you look up really close in there, the inside of link 3 is pushing on the inside of link 4. So I don't care whether you call that a normal force or a tension force, as long as you're consistent. I like to look from a distance and call it a tension force. And so I would label it as tension by 3 on 4. And those 2 forces are equal and opposite by what law? Shout it out.
Third.
Yeah, if you just shouted out third law, slap yourself silly. Slap yourself silly. Look at those forces. They're not married. They're married, but they're not married. Look, they're not the same flavor. One's a tension force and one's a gravitational force. They don't have the same indices reversed. They have nothing to do with the third law. Those are equal and opposite by second law. And when you invoke the second law, you have to qualify your statement. I would say those 2 forces are equal and opposite by second law, finish your sentence, with 0 acceleration. That diagram has to scream balance, and I've only got 1 force up and 1 force down. So they have to be equal in magnitude, okay? Now we can use Newton's third law. 3 cannot pull up on 4 without 4 pulling down on 3 just as hard. I put tick marks to show that that's part of a married set, a third law companionship, if you will. Now I ask, what else touches 3 besides 4? Well, that's 2. And it pulls up with a tension force. Now, if this weight force is 3 newtons, then this tension force is 3 newtons. By third law, this tension force is 3 newtons. So this tension force has to be 6 newtons. Again, by Newton's second law with 0 acceleration. All my force up has to balance all my force down. Now I use Newton's third law again. 2 cannot pull up on 3 without 3 pulling just as hard down on 2. I use 2 tick marks to indicate that those are part of a matched set. I then ask what else touches 2. Well, that would be 1. And if this is 6 newtons and this is 3 newtons, this must be 9 newtons. And then I use third law again. If 1 is pulling up on 2, 2 is pulling down on 1 just as hard. I use 3 tick marks there. And then finally the rope pulls up. If this is 9 newtons and that's 3 newtons, this would have to be 12 newtons, which just happens to be the weight of all 4 links combined. Okay? Now in that homework problem, you were asked in your 4 diagrams, how many third law companionships do you have? And the answer is 3. Okay, there is a third law companion to that tension force by the rope, but you don't find it on one of these diagrams. You find it on a free body diagram of the rope, and that's not one of your 4 diagrams. Okay, so it's 3 sets of third law pairs. See if your neighbor followed that homework.
Yeah.
Yes. Oh, they have the same indices reversed, and they're the same flavor of force. If one's a normal, the other's the same. Oh, this one is by 1 on 2, and this is by 2 on 1. The indices are flipped. Okay. Now, folks, I came back to my office and found this sitting on my keyboard, a plastic pear. And when I investigated, there was this in there. There's forces. And suddenly I smiled and said, oh, forces come in pairs. Oh! Someone in my department has a sense of humor. Not all of you. Okay. Now, suppose I take a Sprite can and put it on a table. In Montana, this was a Coke can, but this is BYU. Okay. And I ask you to draw a free body diagram for that can. Well, that's simple. There's a weight force, a gravitational force. We label it by the earth on the can. And then I ask, are there any magnets? No. What touches the can? The table. Does it push or does it pull? It pushes with a normal force. Table on the can. These 2 forces are equal and opposite by what law? By second law. By second law. Again, they're not third law pairs. They're not the same flavor. They're not the same indices. They happen to be the same size, but not always. And I can show that by putting the can and the table in a elevator and having an acceleration that is up. Now, really quick, this is review. Is that elevator moving up to the 10th floor or going down to the lobby? I don't know. It could be going up and speeding up, or it could be going down and slowing down. And those both feel exactly the same if you don't have a window in your elevator, okay? So it could be either, but that's old news, okay? What has to change in your free body diagram? Does the weight of the can change? No, that's only diet or exercise. And this diagram has to now scream that acceleration. So that means the normal force has to get bigger, So suddenly we see that those 2 forces can't be a married set. they can't be third law companions. They're not equal anymore. Okay? So what is the third law companion to that normal force? What would it be? What flavor of force? Normal, okay. And the indices instead of table on can would be can on table. And what free body diagram would I find that on? On the table, yeah, okay. It's always the second indice. That's earth on the can, table on the can, they all act on the can, okay? Now, if we we label those with tick marks to show that they are third law companions. There's also a third law companion for this gravitational force. If I draw a free body diagram of the Earth, there will be a bazillion different forces on that. That's a messy diagram, but one of them is going to be a gravitational force. Instead of Earth on the can, it will be can on the Earth, and I'll use 2 tick marks to indicate that those are a matched set. Now here's the big idea, the takeaway. Whenever you are comparing 2 forces on the same free body diagram, on the same dot, you use Newton's second law, okay? That normal force is bigger than that weight force. By Newton's second law, finish your sentence with acceleration up. Whenever you're comparing forces on different diagrams that are the same flavor with the indices reversed, you just invoke third law and stop talking. I have some people say, well, those are equal and opposite by third law and the fact that it's not accelerating, or it is accelerating, or it's Tuesday. No, you just stop talking when you say it's third law. Because if they're equal by third law, they're always equal by third law, forevermore, forevermore. Now, if we go back to acceleration 0, these are now equal and opposite by Newton's second law with 0 acceleration, and these are going to be equal by Newton's third law. Okay, Newton's second law. Questions? Yes, sir.
So just to like clarify, the free body diagram explains how the object is moving.
No, it explains how the object is accelerating.
How it's accelerating.
Yes.
These forces just explain the forces that are acting within that.
Say that again.
And so with ones with the tick marks, that just explains the forces that are acting within them.
Those are the tick marks are indicating which forces are equal and opposite by Newton's third law. Those are the match sets. Yeah. Okay. We had a pretest on Tuesday, and the third question asks you to compare the normal force by the snow on the crate to the normal force by the crate on the snow. How do those compare? Yeah, you hear the sing song, don't you? Those are equal by Newton's third law, equal in magnitude, opposite in direction. Okay? Now, yes, sir. What's that? No. It turns out that whether it's accelerating, not accelerating, Tuesday, it don't matter. If they're equal by third law, they're always equal, whatever they're doing. You saw when Seth and Sage were pushing on each other, the forces changed, but they were always equal and opposite to each other. Okay, it looks like we're ready to go, people. You understand Newton's third law now.